Okay, welcome back everybody. Happy dreary Monday. So again, start on page 43. Don't make me turn the lights on and off. I will. I'll do it. All right, starting on page 43. Today is our introduction to derivative formulas. Looking ahead, this coming class is polynomial optimization, and then the class after that is our project check-in day. Remember, you will get the most out of that day if you are on track in terms of my recommended calendar for both projects. But wherever you are, hopefully you'll make some good progress in class on Friday. I will also hand out a take-home quiz on Friday. Questions on the calendar? Okay, so here we are on page 43. In this class, we see our first derivative formulas. Warning, many of these formulas are not intuitive. Some of them are, but most of them are not. Oh, before I get there, one quick announcement. So I think I had mentioned, maybe I haven't mentioned, in the back of your packet, there's a collection of sample test problems, hopefully preparing us for the first test, which is still a ways away. So in your packet itself, there's an answer key for those sample test problems. Up on Moodle, there's a full color set of solutions to those problems, like step-by-step all the way worked out. And on YouTube, you can find videos of me solving those problems, and I think there's directions in the packet for how to do that. There's also links to the playlists in Moodle itself. But YouTube is only available if you have access to the internet, and if you don't have access to the internet at home, then you might prefer to have like the actual like digital video files. So if that describes you, I will tell you that the collection of all the practice problems videos for the whole semester is 443 megabytes. So you don't even need that big a flash drive. But anyway, if it's something you're interested in, the files live on my computer in my office. So you just find me sometime with a flash drive. Okay, so here we go, notation. We will see this notation formally in a few classes, but if you see d over dx looks like a fraction, and then some brackets, there'll be some stuff inside the brackets. What that collection of symbols means is the derivative of what's in the brackets. The derivative of what's in the brackets. That's shorthand notation for the derivative of what's in the brackets. Okay, so a reminder. One of the things we did last class was in our activity was to calculate the derivative of square root of x. That's our new notation. And we found that it was equal to 1 over 2 square root of x. But there was a lot of work involved in that calculation. Here it is. It involved, we had, let's go here. From this point, we had to rationalize the numerator, which meant multiplying top and bottom by the right thing. And then we had to do lots of distributing up on top, and good stuff happened. Ultimately, the numerator became just h, and then that was able to cancel with the h that was in the bottom. And then finally, we send h to 0 by literally just substituting 0 for h, and we get 1 over 2 square root of x. So today, we see lots of shortcuts. The goal is to get to that answer, but maybe without going through all of this limit calculation and all of the algebra associated with it. Okay, so rule number 1. If c is a constant, then the derivative of c is 0. The derivative of any constant is 0. Hopefully this makes sense. If you imagine graphing y equals a number, you'll graph a horizontal line, and the derivative of that horizontal line is 0 everywhere. Yeah? So, for example, what is the derivative of -7? 0. Good. They'll get harder, I promise. Okay, the power rule. We saw this unofficially last class. Now we're seeing it formally today. If n is any real number, then the derivative of x to the n, this is x to a constant, is equal to n times x to the n minus 1. And so in English, what that means to me is that I'm supposed to bring the power down. So this n comes into the front right there. And then I copy the x, and then I subtract 1 from the power. It used to be n, whatever it is, I subtract 1. It's written as n minus 1. But the key is to subtract 1. So first you bring the thing down, then you copy the x, then you subtract 1. And we'll pause here. All right, so let us apply our newfound power rule here in number 4. First example says find the derivative of x to the 6th. So we bring the power down, 6. Copy the x, there's an implied multiplication in there. Subtract 1 from the power, 5. Done, 6x to the 5th. This power rule works perfectly well for negative exponents as well. So what comes down? -4, we copy x and then subtract 1. 3 or 5? 5. Make sure, like, sometimes they go the wrong way when it's a negative. You are subtracting 1 regardless. -5 is correct. Okay, and then our old friend from the top of the page is this guy. Now, this guy currently does not look like x to a power, so sometimes you need to do some rewriting. So it's really x to the half, but I'm going to copy all of this brand new notation for us because I haven't done the calculation yet. I haven't actually taken the derivative, so I still need to include those directions that say, still we need to take the derivative of this thing in the brackets. And now we can do our power rule. So what comes down? Half, copy x, new power, -1/2. Subtract 1 from that power. And that's it. This answer is perfectly acceptable. I think we saw that, we saw last class, that that 1/2 x to the -1/2 is exactly the same as what we got after doing our entire algebra intensive process up above. They're equal to each other, okay? All right, so that's the power rule. Next up, if c is a constant, then the derivative of a constant times a function, f of x, is the same as the constant times the derivative of f of x. So said another way, if you have a constant being multiplied by some function, you can bring that constant right to the front and it just hangs out there waiting to multiply by the derivative of the function itself, okay? This one's going to be really useful for us. So let's try this and then we'll look at the 2 special cases over there. Number 6, the derivative of -2x to the 5th. So I see a constant multiplier. I see a -2 times some function of x. So I'm going to bring that -2 right into the front. I'll put it down here. -2 times, and then I'm just going to copy all of the other stuff. Still need to do the derivative of x to the 5th. Okay, so the -2 comes to the front. But hey, x to the 5th is one of the things that I now have a shortcut for. This is our new power rule. So the -2 is just hanging out here in the front. And then the derivative of x to the 5th is 5x to the 4. That is the derivative. So that it would be like, you know, like if a problem said square root of 9, you said, oh, that's 3. You've taken care of the square root, right? Like you wouldn't copy the square root anymore because you've done what the instructions are for the square root. So once we have taken the derivative, we don't put the funny d over dx anymore. Okay, and then let's just smush together the -2 and the 5. So -10x to the 4. And with just a tiny bit of practice, you can ultimately sort of skip this step, at least just do it mentally, not bother writing it down and say, okay, I know that -2 is going to multiply by whatever I get for the derivative of the rest of this expression. So the 5 comes down, multiplies by the -2, and you just immediately jump to the answer, right? Just -10x to the 4. Aaron?
Since we're learning rules, are you ever going to have to calculate?
Great question. So the point of the rules is that it allows you to do these problems faster, and it also makes it so that we can do a lot of problems we probably wouldn't even want to ever do all the way out with the algebra. I am going to make you use the slow algebra way, maybe once on the quiz and maybe once on this first test, and then not again. Yeah. Okay. That said, every time we have a brand new function that we want to take a derivative of, we are going to have to go back to first principles, but I think this beginning part of the class is the only time I'll ask you to do that whole limit definition. Okay, special case. Let's take a look at this guy here. So this one is a function on top of a constant. And so in my mind, I can think of that as being like a 1/c times, I should not be using my fancy pen here. I can think of that guy as being a 1/c. I'm still using my fancy pen. Uh, 1/c times f of x. You guys agree? That is the same as this? Yeah. And so 1/c, hey, that's just a constant, isn't it? And so my constant multiplier rule says I can just get that guy hanging out in the front and take a derivative of f and then just hit the final thing with the 1/c. And so when all is said and done, you just take your derivative of f and then the c, is just hanging out on the bottom. It's just still exactly where it was, okay? And so let's take a look at this part B here, x to the 12th over 7. So that 7, I see, oh, that's just a constant multiplier, a constant divisor. So whatever my answer is, it's just going to be something divided by 7. I've taken care of the division by 7, and now it's just the x to the 12th. And that's our power rule. Somebody we haven't heard from yet today? What's the derivative of x to the 12th? 12x to the 11. Good. And it's done. Okay, a couple of things before we move on to part C. First, some of you have seen these derivative shortcuts before and many other derivative shortcuts that we will get to this semester, but not today. And one of those derivative shortcuts tells you how to handle a quotient. It's called the quotient rule. And so soon enough, I think next class, we're going to see that rule officially together, and you could apply it to the x to the 12th divided by 7 because it's a division problem. Quotient rule is one of the messier rules that we'll see all semester. If you are divided by a constant, don't use this like crazy complicated quotient rule that's coming up. It's division by a constant is just that, okay? Don't replace this very simple thing with the more complex thing that's coming. Number 2, when I took AP Calculus as a high school senior, I got a 5 on the exam, and I thought that I knew what calculus was. And I thought what calculus was this collection of derivative shortcut rules. That's what I took away from the class. And it wasn't until years after that that I realized this is, okay, yeah, it's an important part of calculus, but we have been doing calculus for like 2 weeks now, and this is the first time we're doing these shortcut rules. So calculus is about slopes of tangent lines and thinking about increasing and decreasing and solving application problems and interpreting this derivative. This is important, but this is not like equivalent to calculus 1, right? It's just a part of it. Okay, other shortcut right over here. If you want to take the derivative of a constant times x, turns out that it's just the constant. Think about the graph of y equals like 5x. That's just a steep uphill line, yes? Y equals 5x. What is the derivative at every point on this line? It's 5. The derivative is just the slope of this line itself. And so the derivative of a constant times x is just the constant. So what's the derivative of negative 24x? Negative 24. That's all. Okay, when you're ready, moving on to the next page. Okay, another special case here. Derivative of a constant divided by x. Constant divided by x. Turns out it is negative the constant over x squared. You can do it without the shortcut. Let's do the shortcut, and then I'll show you how you can do it without, and then hopefully you buy that the shortcut is worth knowing. If you wanted to do this with the shortcut, it's a constant over x, so the derivative is just negative the constant over x squared. So what's the derivative here? Negative 3 over x squared, right? That's it. It's done. But that rule actually isn't one that you need to memorize. I think it's worthwhile, but you don't need to memorize it. So for example, suppose that we started up here and we tried this thing without our shortcut. So would you guys buy this is the same as the derivative of 3x to the negative 1? Right, x on the bottom is the same as x to the negative 1 up on top. And then we know that the 3 is a constant multiplier, so we can just kind of let that hang out in the front. What happens here to take a derivative? Negative 1 comes down, hits that guy, so negative 3. Copy the x, and then the new power is negative 2. That's fine. And then x to the negative 2 really means x squared on the bottom, right? What's on top? Negative 3. Okay, so how does that compare to our answer? Same. Okay, so you don't need this constant over x. It's not like it's not its own separate rule, but it comes up so darn often that I just have started encouraging my students to just learn it as a separate rule. It's quite useful. Okay, and then down here, negative 5 over t becomes negative the constant over the variable squared. So what is it? 5 over t squared is good. Negating that constant turns it into positive. X, t, doesn't matter, it's just the variable. Okay, and then the last two derivative rules here, they look quite complex. They're actually not bad at all. But in symbols, this first one says the derivative of the sum of two functions is the same as the sum of the derivatives of those two functions. So anytime you see a plus sign between two functions and you want to take a derivative of the whole thing, you get to mentally just separate those two functions out, take their derivatives independently of each other, and then just add the derivatives back at the end of the day, and that's your answer. So let's see that in practice. It works just as well for subtraction. So let's see that in practice here in number 10. It says, let's find the derivative of this polynomial, and then we'll use that to find the equation of a tangent line. Okay, so let's use some good notation. F of x, that means the thing that I want is f prime of x. And I'm going to look up there, and I see an addition sign and a subtraction sign and an addition sign. And I'm going to write those here in the same order that they appear. And then, I mean, you don't need to do this. I'm just doing this because it's our first time. But then I'm going to put into these blank spaces the derivatives of each of my four things. Fair? Addition and subtraction says you can just completely separate and then fill in the derivatives separate from each other and just add and subtract at the end, just like they were in the beginning. Okay, so let's start with the first one. Negative 5x to the 4. 4 comes down, makes negative 20x to the third. Subtract 1, so that one's done. Next one, 2 comes down, makes 14x to the first, which I'm not going to write. Negative 3x, that's one of our special ones. The constant times x is just the constant, so what is it here? It's just 3, and the negative is just kind of copied it as a subtraction symbol. Okay, and then the last one, 2 to the third. 3 comes down, copy the 2, subtract 1 from the power. Is that right? Right, 3 comes down, copy. What happened? It is 2 to the third, so what's the derivative? 0. It looks like I could apply the power rule. It's got a power on it, but this is not x to a power. This is a number to a power. 2 to the third is just another way to say 8. The derivative of 8 is nothing. So you cannot apply the power rule to everything that looks like it has a power. It's really specific. Right? X to a power, that's what the power rule applies to. Okay, so there's our answer. We don't even need to write the plus 0, but do we see the blue plus and minus signs and how that's the application of that rule up above? It says addition and subtraction, really nice. We're going to see next class, multiplication and division, not nearly as nice as addition and subtraction. Right, so that's coming. But for addition and subtraction, we get to do what is very natural for us, and that's just separate. Okay, so there's my derivative, and now we'll do this last piece here. It says find the equation of the tangent line at x equals negative 1. Okay, so to find the equation of any line, for sure I need its slope. And so the slope is the derivative, right? The derivative is the slope of the tangent line. But up above, we calculated the derivative for a generic x. Now I want the derivative at a particular x. What x? Negative 1, because that's what is given, okay? So now we plug negative 1 into the derivative, and we get a numerical answer. Negative 20, negative 1 cubed, plus 14 times negative 1, subtract 3. 20 plus 11, 31. I'm going with 31. Anybody get something different? Okay, so that 31 is the slope. Something is not right. What did I do wrong? 20. Oh, it's 20 minus 14. It is 20 plus 14. My fault. My fault. Oh, I mean, good catch. That's just. So what is it? 20. All right, so 3. 20. Okay. Yeah, good. All right, so the slope there is 3. And now we want to find the equation of the tangent line, but to find the equation of a line, I need not just the slope, but I need a point. And at the moment, I have partial information about my point. It's at x equals negative 1, but what I don't yet have is the y value. And so we still need the y value. So how do I calculate the y value at negative 1? No more changes, no slopes. How do I find the y value at negative 1? Negative 1 into f of x. right? This is not a calculus question. This is just find the y value, which means plug into the function. So f of -1 is the next calculation. So we plug now into the original, not the derivative. So this is going to be our y value. So -5 times -1/4. I got 13. Or possibly I'm just tricking you to see if you're paying attention. Anybody else get 13? Or something different than 13? 13? Okay, so let's just summarize. We now know that the slope of our tangent line is 3, and that a point on our tangent line is -1, 13. And now it is like a college algebra type problem, right? Like there's no more calculus left in this problem. It's like do a y equals mx plus b kind of calculation and write the equation of your line. And so we're actually going to stop this one here just so you can jump into the activities. I'll just put y equals mx plus b dot dot dot. Like that's the rest of that problem. But I will point out that we plugged the -1 into the original and into the derivative. And we did that for like very specific reasons. You plug -1 to the original to get the y value. Plug -1 into the derivative to get the particular slope. Really common mistake that I see folks make is that they say, okay, I'm going to get my point here. And I know that the derivative is the slope of the tangent line. And so sometimes I see students take this entire thing right here and copy it, x's and all, in place of the letter m. And that's like, it's understandable. It's an understandable mistake. The derivative is the slope of the tangent line, but we're never going to be taking an entire like expression with x's in it and throwing it in for m. M is supposed to be a number at the end of the day. The derivative is the slope of a generic tangent line in the first line. We wanted the slope at -1, so you got to plug that guy in. Okay, any questions on the process? Okay, so go ahead and jump in on the group activities. At some point, I will call us all back together. Let's see how far we can get here. Or so. So I wanted to make a couple of observations about what I've seen. This topic right here is a really important one for us, and we got to make sure we get it down. We're going to be doing a lot of derivative calculations with these shortcut rules throughout the whole semester. Couple of observations. So first of all, I am a big fan of using notation, not for the purpose of like giving me an opportunity to take points off on a test or a quiz, but for the purpose of you communicating effectively with the reader. You are writing and creating mathematics, and it is your job to not just get the final right answer, but it's your job to communicate it effectively. And as you get higher and higher in the math sequence, the expectation for how well you communicate also rises. And so, for example, for this guy right here, the first step was to rewrite, yeah? So we have to take this thing and make two different fractions, and then we have to take this thing and clean it up. And so it is currently now in a form where I can take a derivative, but I've just got floating stuff. These two blue things are not connected to each other, and they're not connected to the original problem until I put, hey, this is really just f of x. And just writing those 1, 2, 3, 4, 5 symbols like makes a complete thought now, right? Takes stuff that was floating and tethers it firmly so that the reader can understand where it came from. This next one, is it f or is it f prime? This is still f equals, right? Okay, if you are just saying something is equal to what's above, you don't need to rewrite the f of x every time. Just equals, equals, equals. But then when I'm ready to take a derivative, that's where we change thought and we start over and we say, hey, f prime equals, and the derivative of x is 1, and a constant over x is negative the constant over x squared, right? That is a complete thought. Without the f prime of x equals, it's not connected at all in any way to the previous work, but now it is. And then you would need to calculate f prime of 1, and you would also need to calculate f of 1. Some students like to just jump right in with the calculations. Oh, I know I'm supposed to plug 1 in, and they start doing the arithmetic. But that leaves the reader in a very dangerous place, especially when the reader has a red pen and is anxious to take points off of your paper. Okay? So just a couple of pieces of notation. It's not there to get in the way. It's not there to be a burden. It's there to help you effectively communicate. It's supposed to help. Oh, the d over dx is an equivalent form for this f prime of x. It was just more convenient to use that one in the demo. Okay, so I think that is good right there. So what we are going to do is we're going to move on to this page right here, 48. Everybody jump to 48. So let's take another quick look at our calendar here. So I don't know if you've been noticing, but the sections that we cover the books in is not at all the order that the author intended. So the author wrote 1.1 to be followed by 1.2 and 1.3, and eventually you finish chapter 1 and start chapter 2 and chapter 3 and chapter 4. And you can see that the first day we were right there. But the second day we were already starting chapter 2. Then we went back to chapter 1, then back to chapter 2, more chapter 2. Today is chapter 3, and next class is 4.2 and 4.3. And it's probably felt like a sprint for some of you, and I can totally get that because we have been sprinting. Maybe you didn't know, but I knew from the first day we've been sprinting to this Wednesday's coming class to get to that section in chapter 4. And all of the order of the stuff that's out of order here that we've done so far has been with the intention of sprinting to next class in this chapter 4. And in chapter 4, we do some of the harder problems in the entire calculus course. And polynomial optimization is something that we're going to thread all the way throughout the semester, including on all 6 of the projects and the 2 that you're working on right now. You are trying to like maximize the joint happiness of Frank and Ellen. That's an optimization question. You're trying to minimize the cost for the trucking, like the gas and the labor, right? That's another optimization question. So we've been sprinting to this section 4, and then we're going to go back and we'll review some pre-calc stuff, and then chapter 2, we'll sort of go back and forth and review pre-calc as needed. But I know that next class is a doozy. It's in chapter 4. It assumes that you've been in Calculus 1 for 2 months, not 2 weeks. And so we're just going to jump in a little bit here to the next class. Just grabbing a few minutes here I think will help next class. Okay. So in this class, the homework is not going to be assigned. There's just one homework assignment. We're just getting a jump start on Wednesday's material. In this class, we find relative and absolute extrema for in-context problems. For the function pictured, identify the x coordinates of all local maxima and minima. Okay, here we go. Local maxima, x equals. So looking at my graph here, I've got a bunch of points labeled A, B, C, D, all the way up to J. Some of them are local maxima, meaning they are higher than all the points nearby. So where's the farthest left one that you see that's is B? So x equals B. That's one local maximum. Moving on, any other local maxes? F is another local max. Because F is higher than the points nearby. I'm not saying F is the highest point anywhere. The point at B is a lot higher than the one at F, but if you are standing at F, you are on a mountaintop, right? It might not be at the whole top of the mountain chain, but you are on the top of a mountain. And so we call that a maximum, a local maximum. And then local minima, same idea, but other upside down. So x equals D, that's a min. And also H, that's good there. And something very special happens in terms of the tangent lines at all 4 of those points. So at x equals B, the tangent line is horizontal, yeah? And at x equals D, the tangent line is horizontal, and at F and at H. And so at all of our maxes and mins, the tangent line is horizontal, meaning the derivative is equal to what number? 0, right? So that's a connection that we're making here. It turns out that there are also places, there are other kinds of places that you might see where you have a max or a min. So in this picture right here, there is a local minimum at that bottom point. Is the derivative 0 at that bottom point? No. What can you say about the derivative at that point? It doesn't even exist, right? The derivative does not exist there. So it turns out those are the 2 places where you're going to find local maxes and mins. You're going to look for places where the derivative is 0, and you're going to look for places where the derivative doesn't exist. Yeah. And so here is our Here's our conclusion. It's got a name. It's called Fermat's theorem. If f has a local maximum or minimum at c, c is just the x value for a particular for a particular point, then either f prime of c is 0, horizontal tangent line, or f prime of c does not exist, like in a cusp. Okay, those are the only places we have to look for local maxes and mins. And on the very first class, we defined, or we loosely defined this phrase, critical number. We said a critical number is a place where the graph is flat. Okay, so now we've got a more precise definition. We call c a critical number of the function f if f prime of c is 0, flat, or if f prime of c doesn't exist, just like in the previous example. And so Fermat's theorem now changes. It says, hey, the only place you have to look for local maxes and mins are the things that we are now calling critical numbers. Critical because they are critical to understanding the behavior of the function. Right? These are important points. Okay, moving on here. Suppose that we had this problem. Identify the x coordinates of all global maxima and minima on this closed interval a to j. Global compared to local. Local just means, like a local max, it means you're higher than the nearby points. But the global max is the absolute highest point any place on this interval. Okay, so global is a much stronger condition. So let's take a look. We're looking from A to J, same picture from up above. I will highlight it, maybe purple there. Okay, A to J, so that's from this point out to this far right point and every place in between. Where is the absolute lowest point anywhere on that interval? Is it D? Yeah, that's the lowest point on the interval. If I let the graph go farther left, I'll find lower points than a D, right? But we're cutting it off. And so between A and J, for sure, D is the lowest point of all the ones available. Where's the highest point between A and J? Is it at B? Actually, it's at J. J is definitely higher than B. All right, so we have found our global max and our global min. Let's write down those coordinates. So what did we say? D and J, right? Okay, so where are we here? So the global max is at x equals j. That was the highest point. And the global min is at x equals d. And these two x values were important for entirely different reasons. D is important because it's a critical number. What's the derivative at d? It's 0, horizontal tangent line. So d is for sure an important point. Why is j an important point? It does have a slope to it, but like if I move a tiny bit to the right of j, don't I get a higher point? There's nothing special about j, right? J is just a random point up there on, like an upward steepening graph. But why was j important for this problem? Yeah, I gave you an interval, and one of the endpoints of that interval was j. And so the only reason j was important in this problem is because I artificially made it important by making it one of my two endpoints, right? So there's nothing special about j except it happens to be like an artificial cutoff for this particular problem. So if we are looking for global maxes and global mins on an interval, there's only two candidates, only two kinds of points that we have to look for. We're looking for our critical numbers. I've got 4 of them with my green tangent lines, right? Those were all candidates for the highest and lowest points. And then I've got my endpoints, A and J. A was not the highest or lowest, so it wasn't a winner. J, artificially, yes, it's the highest point in this interval. So that is here. Number 7, to find the absolute extrema. Extrema is the plural word for maxes and mins together, extremes. To find the absolute extrema of a continuous function on a closed interval. I'll underline that. It's a standard kind of problem, closed interval. You're going to evaluate the function at each of the critical points and at the endpoints, critical points and endpoints. And then we're going to pick the highest y value that we see, and we're going to say that's the global maximum. And we're going to pick the lowest y value we see and say that's the global minimum, okay? So we are going to end here, and we are going to apply that process in number 7 to number 8 first thing on Wednesday, okay? Oh, one last thing. Some of you have had like a year's worth of calculus in high school. Some of you have never seen calculus before this semester. So especially as you are learning these derivative rules, you are going to see very different abilities here in the beginning from the people that have been doing this for a year and the people that have been doing this for half an hour. So be patient with yourself if you're one of the half-hour people, And don't feel bad that the person sitting next to you can like zip through these derivative calculations. There's a lot of different experiences here. We will get everybody where they need to be. See you Wednesday.